Alright guys, so today we're going to talk about the Taylor and Maclaurin series. So these two series are going to be used, well, they're essentially the same, but due to historical reasons we call them different names. But this is going to be a way by which we're going to find the series representation or power series representation of a function as we did before, like that. However, we are not going to use the geometric series to accomplish this. We're going to use the derivative. So let's say, for argument's sake, that we can actually write these two equal to each other. So let's change that arrow for an equal sign, and let's see what happens. If that were to be equal, what happens when I evaluate the function at a? Well, let me write out a few terms. So when n is equal to 0, this goes to 0, and I get just c naught, let's call it. Then the next one is going to be c1 x minus a to the power of 1 plus c2 x minus a squared plus dot, 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 all of them. And I'm going to evaluate this at x equals to a. Okay? So when I do that, notice that this becomes 0 because I get a minus a. This term becomes 0. So the tail end of my series, it all cancels out. And I end up with that f of a is going to be equal to c naught. Okay? Now, if the functions are the same, you would hope that their derivatives also are the same. So I'm going to take the derivative here and evaluate at a. And what I'm going to have is term by term, I'm going to have the sum as n equals 0 to infinity of, and when I take my derivative, n times cn x minus a to the n minus 1. I just took the derivative of this expression here, dropping the n, and then subtracting 1 from the exponent. But when I evaluate this at x equals to a, let's write out a few terms. All right, so the first term is going to disappear because when n is equals to 0, I get 0 there. And so this is going to become, I'm going to start writing here, n equals 0 cancels. N equals 1, I get c1, and then x minus a to the 1 minus 1 is just c1 because that's to the power of 0. Then I get n equals to 2. When n is equal to 2, I get 2 c2, and then x minus a to the power of 2 minus 1, which is 1. And then I get the next one is going to be, I'm going to be taking the value at n equals to 3. So I'm going to have a 3 c3 x minus a to the power of 3 minus 1, 2. I'm just taking the derivative term by term. And then I'm going to evaluate that at x equals to a. Notice now that the higher order terms cancel, because when I evaluate x equals to a, I get a minus a, which is 0. Same here, and all of the tail end of the series also becomes 0. So I'm going to have that f prime at a, sorry about that, now I cannot cap it, is going to be equal to c1. All right, let me pause here for 1 second. I'll pick that up. All right. So never a dull moment, I suppose. So let's go ahead and take our second derivative and see what happens. So whenever you take the second derivative, and I promise this is the last one, then we're going to write a formula, because what I'm doing secretly is I have this, I'm writing it as c naught plus c1 x minus a plus dot dot dot. You see, I already know what c naught is, and I know what c1 is. C naught, as we compute it, is going to be f of a, and c1 is going to be f prime of a. As it turns out, c2 is going to be related to f double prime. So I'm going to be able to write this in terms of the derivative of the function. Ruined the surprise, didn't I? Anyways, but if you take the derivative of this expression here, you would have the sum from n equals 0 to infinity, and then you take your derivative of that. So it's going to be n times n minus 1 times cn times x minus a to the n minus 2. Taking the derivative term by term. So I just took the derivative of this expression here, dropping the n minus 1, subtracting 1 from the exponent. And then when I evaluate it at x equals to a, what do I get? Well, let's take a look. When n is equal to 0, this goes away. When n is equal to 1, this expression goes away, 1 minus 1. And so I start with n is equal to 2. So I get 2 times 2 minus 1, 1 times c2, x minus a to the power of 2 minus 2. I should have not written that. That's just going to be to the power of 0, which is 1, plus the next one, when n is equal to 3, I drop the 3, that one right there, 3 minus 1, 2, times c3 times x minus a to the power of 3 minus 2, 1, plus dot, dot, dot. And now you know that when x is equal to a, these terms will cancel. And the whole tail end will go to 0. So I get that the second derivative is going to be 2 times c2. So from here, I can solve that c2 is f double prime of a all over 2. Now, the next time I take the derivative, I'm not going to solve it, but I'm going to take the derivative just so you see it. I know I said I wouldn't take it again, but here we go. Take the next derivative. So you get n times n minus 1 times n minus 2 times cn. I forgot my cn. I'll put it at the end. N minus 3. So what happens is you just keep multiplying one less. So here I had technically a 1 times c1. Here I have a 1 times 2. The next time I'm going to have a 1 times 3. The next time 1 times 3 times 4. And what is that going to be? Then that's going to give me that cn is going to be the nth derivative of the function evaluated at a over n factorial. Because I'm going to be multiplying those terms. In this case, 2 factorial is 1 times 2. 3 factorial is going to be 1 times 2 times 3. And so forth and so on. So putting this together over here, I can write my expression. So I'm going to leave this here, and I'm going to plug it into this equation, and we're going to get what is called the Taylor series for that function. And the Taylor series for that function centered at a. All right, I'm going to go ahead and erase all this and write it down. All right, so we put down the coefficients that we computed, and this is going to be called the Taylor series. Of f, or centered at x equals to a. Whenever you center your series at 0, that it would be called the Maclaurin series. So that's the distinction between them. Now, there's something I just did and I didn't even talk about. I just said, well, you take the nth derivative. But who guarantees that the function can be differentiated and evaluated at a over and over? So we should have a condition of differentiability. So the functions that can be differentiated as many times as you want are called smooth functions. So we're assuming that f is a smooth function, at least around a, in an interval near a. And of course, the next question that we will have is, well, once you have a series of this form, what can we say about the convergence? Is it going to be, or the intervals or radius of convergence? And so those are the questions we're going to talk about. So let's start with an example. So let's compute the Taylor series of the function f of x equals, let's do a typical one, natural log of x, centered at 1. And we did this one, if you're in my class, we did it in the Zoom session using the geometric series. Now we can do it using the Taylor series approach. So what do we need? Well, look at what we have here. We need the derivative of the function, so we would need to find what is fn. So we're going to start evaluating f1. That's the first thing we're going to do. F1 is f of 1, sorry, is going to be f or natural log of 1, which is 0. So that's our first coefficient, is 0. Now I need my first derivative, but I want to evaluate it at 1, so I made a mistake. Let me erase there. Evaluate it at 1, and that's going to be 1 over x. That's the derivative of your natural log evaluated at x equals to 1, which is going to be 1. Let's do it again. So the whole point here will be to find a rule that gives us eventually the nth derivative of the natural log evaluated at 1. That is our goal. So let's take a look at and see what happens. When I take this derivative here, I'm going to have the negative 1 over x squared. That's what you get when you think about 1 over x as x to the negative 1. X to the negative 1, then you drop the negative 1 here. Minus 1 in the exponent becomes negative 2, so it becomes that. Evaluated at x equals to 1, so that becomes negative 1. F triple prime. So the third derivative. Now I'm taking the derivative of this one. So negative 2 is going to be the exponent times negative is going to be 2 over x to the negative 2 minus 1. So x cubed here. Evaluated at x equals to 1. That's going to be 2. And the pattern will start emerging. Let's do the fourth derivative. And I think after that we can kind of see what's going to happen. So the fourth derivative at that point, and should I have done Roman numerals or just straight up 4? Now I did Roman. Anyways, that will be sufficient though. All right, so now we're going to take the derivative here. So I'm going to have negative 3 times 2. So it's going to be 2 times negative 3 is going to be, let me write it like this, 2 times negative 3. I'm going to write it like that. And there's a reason why. So give me just 1 second and I'm going to explain why. So that's going to be negative 2 times 3. Now, why is that? Remember, I'm going to have an n factorial here. So whenever I divide by my n factorial, things are going to cancel nicely here. So let's go ahead and look at what happens when I divide by n factorial. And I want to leave my formula on the screen, and I want to evaluate this. So let me see how I'm going to play with the space. All right, so let me move over here and try to figure out what my fn, the nth derivative of f at 1 over n factorial will look like. This is what I need. So this is going to be my question mark. Let me evaluate a few of them. Let's start with the last one. That may be the easiest one to look at. And that may give us everything I need. So the fourth derivative at 1 over 4 factorial is what? Well, I'm getting a negative 2 times 3. I was about to lose that cap again. Divided by 1 times 2 times 3 times 4. So what is going to happen there, as you can see, the 3 cancels and the 2 cancels, and I get negative 1/4. That's kind of nice. You see, I have the fourth derivative, and I get negative 1/4. Now let's go ahead and try to evaluate this one. f1 over 0 factorial. That's going to be 0 over 1, which is 0. Okay, not too bad. Let's try to find out here f prime at 1 over 1 factorial. That is just going to be 1 over 1 factorial, which is 1, equals 1. Now this one, let's try to compute the second derivative of 1 over 2 factorial. And that would be, the second derivative at 1 is going to be negative 1 over 2. So you see I have 1 over 1, negative 1 over 2. Let's see if this one becomes 1 over 3. And I know it's going to be that. But I'm trying to add a little drama. So when I look at that, I get a 2 over 3 factorial, which is 1 times 2 times 3. So that 2 cancels. And if I can fit this here, it gives me a 1/3. So you see I'm getting 1, negative a half. 1/3, negative a fourth. So it seems like I'm going to have negative 1 to the n plus 1. You see, the even numbers are getting an odd sign, or sorry, a negative 1 to an odd power. So I need an n plus 1 over n. And if you check, if you keep taking derivatives, that rule will be satisfied. So for the natural log, which is the one I'm trying to compute, let me erase this and I'm going to plug my value here and I'm going to get my Taylor series. All right, so now we can plug that in here. So for the natural log, it was going to be f of x, which is the natural log, is going to be written in terms of the sum. Let me start it at 1. You say, why 1? Well, because remember that I erased it right now, but remember that the constant term c0 was 0. So I can start at 1, and I can write it like this. I can write it as negative 1 to the n plus 1 over n times x minus 1 to the n. Now, why did I know 1 minus 0? It's because I was going to divide by n. And that would have given me a 0 in the denominator, so that would mean that I have a wrong formula. It wouldn't have worked. So now my next question is, when does this converge and when does this diverge? So at this point, I have to do a ratio test. So this, I have a power series expansion. Now I gotta find the interval and radius of convergence. And to do that, I'm gonna do my ratio test. So I'm gonna do the limit as n goes to infinity. And remember what you do, you have to have the absolute value, so this one will go away, of this evaluated to the n plus 1. So the negative 1 we don't care about, but I do care about this x minus 1. X minus 1 to the n plus 1 over n plus 1. And I'm going to multiply times the reciprocal. I could have divided by the nth term, but I'm going to multiply times its reciprocal. The reciprocal of this expression is going to be n over x minus 1 to the n. Excuse me. And as we said, we can cancel n of them and just be left with 1. And that doesn't depend on n, so I can pull it out of my limit as the absolute value of x minus 1, and then the limit as n goes to infinity of n over n plus 1. Now, this is a rational expression with degree 1 in the numerator and denominator, so the limit is the ratio of the coefficients, therefore that limit is 1. So I get that this limit is x minus 1, and this better be less than 1. All right, so now we just have to write our interval of convergence. So my center is going to be 1, that's the center here. My radius is 1 as well, radius, center. So I go 1 to the right, 1 to the left. So my interval of convergence for this series is from 0 to 2. That's where the expression is valid. Now, if you were to plug 0 directly, well, you have a problem because you have a natural log of 0 that's undefined, so that you don't even have to check for that endpoint. If you plug 2, you get something that is going to be alternating, and you're going to have negative 1 to the n plus 1 over n. That's going to converge just conditionally at x equals to 2. So at x equals to 2, you could close this interval as well. But now I wrote the open one. Remember always to test your endpoints when you're doing ratio test. All right, and that's going to wrap it up for us for this video. I'm going to make another video with more examples. It's just these examples take a little bit longer, so I'm going to try to separate it in several videos. All right, thank you for watching, and I'll see you next time.